Welcome everyone. My name is Doug Schaefer. I'm the CDT project lead. I've been the project lead since 2007. And I've been involved with the CDT project itself shortly after QNX originally contributed it. This is when I was working at Rational back in 2002. So it's been many years. I think this year is going to be a really exciting year as we start to look at what we're going to work on next. And really the focus of this talk is one of those major things, and that is adopting the language server protocol and what that means for C++ language services and how it compares to what we have today in CDT. So I'll quickly go, this is mainly a Java conference. I want to kind of give a little plug for C++, why you'd want to use it. Kind of talk about the latest standardization efforts that are going on around, and they're starting to call it modern C++, because it's much different than what you probably got used to 10 years or so ago. Then I'll just go through what the language service is and give a few demos of stuff. So where is C++ today? A lot of these, I got some charts from a survey that was done by the ISO C++ Standards Committee. So it's kind of it's a little bit small, but really where we see C++ a lot today is a lot of those, traditional places, communications equipment, a lot of the big communication vendors. Some of them participated in CDT in the past, are using C++. Developer tools, interesting enough. So the Clang compiler itself is written in C++, and it uses all the latest cool stuff. And regular engineering things, industrial automation and embedded and IoT. Constrained devices kind of things. Also gaming. There's a lot of there's a big C++ community around game engines and that. So take a look at what people are building C++ applications for. A lot of it's Linux, because Linux, a lot of the Linux apps are based on GNOME and Qt, and so a lot of C++ there. Windows, surprisingly enough, is still a lot of C++. And probably a lot of that is the gaming world, because the survey was a bit slanted towards expert C++ developers. Interesting enough, we actually, we used to have one of the committers for CDT was from Google, where they managed a lot of their services are written in C++ just for scalability and speed. Which IDEs do they use? So this has been one of my main focuses in the last few months. So Visual Studio is still the king, and as much as we try in the CDT world to catch up, and in a lot of ways we were actually ahead of Visual Studio as far as feature content. We had content assist before Visual Studio did, but it's still the king. Interesting enough, Vim is second. So we still have a lot of C++ developers that are just using editors. They're not interested in the big behemoth IDEs. They just want a slim, streamlined environment. And that's why Visual Studio Code is also climbing up the charts. And there's some interesting things going forward with Visual Studio Code as far as bridging the gap between editors and IDEs. Qt Creator, which is the IDE that the Qt team build, kind of eating their own dog food. And Qt developers, that's their main development environment. They don't, as much as I've tried to get them to use Eclipse, Qt Creator is still really their main environment. Then there's a whole bunch of others, and actually Eclipse is in that second tier kind of with the rest of the bunch. We do know, CDT and the Eclipse C++ IDEs are popular. But just don't have that energy as the big guys do. So one of the other interesting things to so this whole concept of you know, C++ is pretty old. It's been around a long time. So when I first started writing C++, this was like in the mid-90s. And, you know, the language, it was just a slight addition on top of C. And it was done that way on purpose in order to make it easier to adopt. And that's why, you know, it ends up being the most popular object-oriented C-like language. But at some point around, it stayed that way for a long time, and then people kind of, it was hard to write good C++ programs. There's a lot of ways that you can mess yourself up, especially with pointers and you know, unconstrained buffers, buffer overflows and all that. Kind of comes from how easy it is to make sloppy code. So with C++ 11, it was kind of, people were basically they started interesting new concepts to try to make that better. And I'll go through a bit of that. But as you can see, there's C++ 11, and the modern C++, as they call it, is kind of where everybody is pretty much at. And every 3 years they do a new standard. And you know, this market is traditionally conservative, so it'll take a while before features that are introduced in the latest standards get into everybody's hands. So we got, you know, as a C++ IDE, you know, we got to deal with that. There's so many different versions, and we need to be able to support all those. So quick overview of what modern C++ is. And basically it's focused on, you know, it's mainly focused on resource management. So in traditional C++, you would write, you know, circle pointer p equals new circle, for example. And then later on, you forget to delete that, where you pass the pointer off to somewhere else and you're expecting them to delete it and they accidentally don't. There's a lot of new, using a lot of the C++ generics, there's a lot of new capabilities as far as managing that. And I'll go show an example here in a minute. And then a lot of this is coming from the standard template library. I remember back in the early 2000s, whatever, it was kind of a joke, the standard template library, because it was so huge and hard to use, and you didn't trust it. You didn't trust that it would be, you know, optimized correctly to something small. But they spent a lot of effort, and a lot of the standardization effort is around the standard template library. The containers, for example, are very feature-rich and really manage the resources that so you can create a vector, and you can, you know, once you put something in a vector, you can be confident that it's going to be managed properly. And the same with strings and that. There's a whole collection of algorithms, so generic algorithms that do things like sorting and searching and stuff like that. Lambdas came to C++, I think that was C++ 11 when they first landed. So C++ has had lambdas for a long time. And, you know, there's an example there. Basically, you capture variables from the calling environment, and it'll get passed parameters from the like myfunct. And actually, if you don't capture any variables, it actually turns into an anonymous function. So it actually interfaces well with existing C code. So that's pretty cool. And recently, things like range-based for loops, like, you know, we're used to in Java, those are now available in C++. And we also have auto typing, which so you don't have to. So the iterator over a vector, which is this big long vector colon const iterator colon whatever. You don't have to worry about that stuff anymore. And the IDEs are smart enough to be able to determine what type that X is going to be, and if you hover over it properly, you'll get to see it. So there's a lot of new language features, but how do you use them properly? And so there's it's part of it's not really part of the standard, but a part of what Bjarne Stroustrup, the inventor of C++, and this guy named Herz Sutter, who works for Microsoft, is kind of a languages architect. So they're basically managing this list of C++ core guidelines. And really it's an aim to help developers understand how to use these features properly. So I definitely recommend taking a look at that when you're writing C++. And there's a lot of interesting rules of how to manage resources in that. And there's actually tools that will take a look at the code and analyze your code against these rules and give you suggestions. So this is an example. They all have magic numbers. Like this is R.1, which is it actually has a longer title, but it didn't fit on my slides. But basically around resource management. So this is a function that takes an X pointer and some destination. Then basically you're going to open a port and send that X down the port. And basically it's locked in a mutex. But as you can see, there's in this, this code, there's a lot of opportunities for things to go wrong. So if something happens before that code before send that causes an exception, it's going to bail out, and it's going to miss the unlock, and it's going to miss the delete and the close port. So you're going to end up leaking resources, and even worse, you're going to get the mutex is going to stay locked. So your code becomes pretty much dead. And in X, you've leaked the X because you didn't get to the delete statement. But with using the new modern C++, basically that's mitigated, and actually the code ends up being a lot smaller. So it's really using, creating little objects which actually optimize out to nothing to manage those resources for you. So in particular, the standard template library has like a unique pointer class which manages the pointer. So when you call this method, you know that you're passing ownership of the X to this function. And when this function exits, it's going to actually do the delete as part of the destructor for the unique pointer. The same thing with the port. So that'll do an open port, and when the function exits, or either at the end or due to an exception, the destructor of port will clean up the port. And even with the mutex, there's a class called lockguard, which will lock the mutex, and then again, on exit, it'll undo the unlock. So it's actually less code, and it's a lot safer. And this is an example of the port, and this is kind of the example of how it's done. Basically, you put the smarts in the destructor, so when the stack unwinds, all the destructors get called, and everything gets cleaned up. And you have a cast operator to port handle so that you can basically plug this class into anywhere that you'd use a port handle. And there's even magic stuff. So in order to make sure that this port class, the stuff in this port class isn't copied, you can actually delete the copy constructor and the assignment constructor. So if someone tries to assign this to another variable, it's going to give you a compile error because that method's been deleted. So that's new stuff. And I took a long break from C++. I was focused on doing other things in the C++ IDE, but working in Clang in the last few months on the language server, it kind of opened my eyes that, wow, the language has changed a lot. And it's a lot easier to work with once you understand all these different concepts. Interesting uses of C++. So I kind of want to show a couple examples of what people are using C++ for. The first one is Arduino. It's something I've shown over the last couple of years, and I've actually the CDT now has support for programming on Arduino boards. And these are really very resource constrained. I actually have one here, the Arduino Uno. It's kind of one of the lowest capable boards. It's kind of the biggest. That's a lot of blank space. But there's things like, you're talking about like K, you're not talking about big or gig. You've got 32K of flash, so your programs can't be bigger than 32K. You only have 2K of RAM, so you can't have too many local variables and stuff like that. But they're very capable devices. It has traditional embedded system I/O capabilities. Lets you hook up to different devices and different sensors and just LEDs and all sorts of different really interactive things. A lot of people are using these things for like flashing lights and doing even wearables with costumes and stuff like that. It's really cool. The language that they program that in, they call it Sketch, which actually just, it's a very slight subset of C++. Basically, they take care of the 4 declarations of functions for you, so that it's really aimed at new users, but I think it's probably good for them to learn what a 4 declaration is. Declare before you use. And they also just strip off the Arduino.h include, even though when you start using different libraries, you have to add includes to those. And there's some more advanced boards. So there's some boards that do Arduino, but they also have their own SDKs. So I've been using a board called ESP32, which has a pretty comprehensive SDK. It even has stuff like MQTT in it for doing IoT type stuff with AWS, for example. So I'll do a quick show and tell of that. So this example of a Arduino sketch. Basically, all I'm going to do here is have a message come out on the serial console, which goes through the USB serial port, and it'll flash an LED. But when you look at it, you know, this is really just a C++. So the serial port is there's a class for it. And it's actually, and there's multiple levels of inheritance, so that anything that does a print can inherit from this. Oh, that's there. There we go. But you know, again, CDT has support for Arduino boards. So I have a, if you look at the launch bar here, I have the Uno is defined up there, and I can run this little program on it. It'll download the flash. Then you see the message coming out, and the LED is flashing. So again, these a lot of the people using these boards are beginners, but a lot of the people are using, and so the Arduino IDE is very built for beginners. But introducing this to CDT, I found a lot of people like us that are pretty expert at programming, and we want good IDE support, so that, basically make it easier to program these things. So that's actually turned out to be fairly popular, which is cool. The second cool thing I want to show, bring that back up. So WebAssembly. So who's heard of WebAssembly? A few people? Oh, lots of people. So WebAssembly is pretty cool. It basically lets you write in a native language, and then there's essentially assembly code, which is their own kind of virtual instruction set that compilers can compile to. So for C++, with the upcoming Clang version 8.0, which I think is coming out in early next year, it's going to have first-class support for WebAssembly. So you can take the Clang compiler that you got on your desktop, and you can start basically set WebAssembly as the target, and it'll compile for WebAssembly. It's a pretty simple instruction set. It's stack-based, somewhat like the Java bytecodes. It operates in a sandbox, so there's a lot of safety stuff built into this. The interesting thing is that the memory basically when your C++ code is accessing memory, it's actually a JavaScript array buffer. And the JavaScript code that embeds your WebAssembly has access to that. So you can actually share information between them back and forth that way. But it's very simple, a constrained environment. The only values that you can pass back and forth between JavaScript and your C++ code are basically numbers, integers, and floats. Everything else has to be kind of wrapped and handled through the sharing through that array buffer. There's actually an environment called Inscripted, which is a pretty massive software development environment. It has a lot of libraries, and there's actually game engines, like Unity uses that as their runtime for, so when you build a game in Unity, it'll actually generate an HTML version of that, which has WebAssembly that'll run. So I was going to show a quick, try and do this quickly, but there's a lot of stuff. Oh, it's very dark. I'm going to change the theme. Let's make it light. There, now you can see it. So this is regular C++ code. This is using OpenGL, or web. It's actually using WebGL, and I've actually defined interfaces for these things. And basically, you can import JavaScript functions into your C++ environment. Where's the import? Here. No, that's not it. So anyway, you can do things like log and that. But yeah, it's like programming regulars. If this was a C++, if you're targeting a device or a game console or Windows or whatever. And then the JavaScript side of it, or the TypeScript side of it, which is easier to read. Basically, you export a lot of functions into the environment, and so your C++ code can call into these things and run things on the JavaScript side. And then in the end, you get something that looks cool like this. So it's basically it was just a spinning cube, which is kind of basic. The interesting thing is, so this is running. You can see it kind of in the bottom there. There's a frame every 0.08 milliseconds. I took there's a demo, and somebody had showed this written in JavaScript, and I ran the JavaScript version of it, and yes, the C++ was faster than the JavaScript version for about 4 or 5 seconds, because the JavaScript version kept getting faster and faster as the JIT kept fixing up the code. So yeah, basically it was, it's more deterministic, I guess, when it's in C++. And I've been able to mess up the JavaScript JIT by introducing different code structures. So if repetitive tasks, maybe, but if it's going to do a lot of different things, then maybe, yeah, C++ would be an interesting way to go. So yeah, there's some cool things going on with C++ still. It's still a very interesting environment. We have lots of users using CDT. So I'm going to switch gears a bit and start talking about language servers. So CDT has been, it's got a fairly extensive collection of language services. We have, in the beginning, we started with a basic Eclipse editor. For an indexer, we use C tags, which is kind of like a regular expression scanner of your code. Really only properly supports C++ because it doesn't understand things like an inheritance in C++. So we built our own parsers, written in Java. A lot of people thought we were crazy, but they actually turned out to be people have issues with the performance of Java, but we certainly never saw it in our work writing these parsers. And it was good that we hand wrote them, because when you're writing a parser for an IDE, a lot of times you're parsing incomplete code. Especially the things like content assist, when you're in the middle of a line, the middle of a symbol maybe. So be able to properly handle, things that aren't quite fitting into the language properly is very important. For the index, we actually cloned the JDT index originally, which worked for a while. And we did, and the thing is that we did full parsing of the project, so including header files and all that. And this is back before 2007, so CDT was really slow. It took a long time to index big projects, so we had a real big scalability problem. So around 2007, I actually left Rational or IBM and joined QNX. Originally did the CDT, and one of the first things I did was rewrote the indexer. So I have this fast indexer. Basically, it's faster because it does less. So it'll only parse header files once, and it saves the symbol information in a database that I also somewhat handcrafted. But it's really fast. But basically, when you're parsing, we try to get stuff out of the database as much as we can, so that we don't have to re-parse things over and over again. And yeah, that worked out really well. So we took, our biggest example is indexing Firefox, which used to take, 45 minutes to an hour. And we were able to actually get it down to under 20 minutes and just kept getting faster and faster. This big issue though is when you're skipping stuff. So when you include a header file, there's a lot of cases where you're including it with different macro settings, and it ends up being different stuff that you're including. But the good news is that that's not a very common thing. So it was good enough, and that enabled us to get us through. And then again, customers have been and users have been pretty happy with that. In order to parse properly, I'm going to kind of speed up in going through these things. So scanner discovery, you need to understand how the files are being parsed. And this is true with the language servers as well. They have the same problem. Because really, it's the things passed on the command line, the minus i's for the include path, minus d's if you're changing macros, even things like changing the CPU architecture, because it'll result in different built-in macros being defined, and compilers have their built-in include paths. So we need to be able to extract this information. So there's a big chunk of code in the CDT that will parse build output, figure out what the command line is, and then go ask the compiler itself, hey, what are the macros and the include paths that you're using for this file? So that's what enables CDT to properly deal with specific problem environments. And we've been doing a lot of work lately, kind of supporting other build systems, not just the ones that CDT implements itself. So interfacing with CMake, which has the compile commands JSON file, which has the exact same information in it, so we don't have to scan build output. We can just go look in that file. And Qt's QMake actually has a kind of command line API which you can extract information from. So once we had a good indexer, parser, and could parse things properly, we were then able to add new exciting features like refactoring. So CDT refactoring uses the same framework that JDT does as far as being able to, so we ask the AST when we make changes to it with the refactorings to create text edits, and then you get to preview that in the refactoring preview UI. And we have things like standard rename refactoring, even though we're the inline rename in place. And we have some other simple structural refactoring, things like extracting constants and chunks of code from a function, creating new functions and like stuff like that. And it's full extendable, and we know there's a lot of people working on refactoring in CDT now, or there's this university in Switzerland that are doing some really cool things, and they actually have a product where they have a whole bunch of other refactorings that they've done to help support their students. CDT also has code static analysis. So this is more complex things than what a simple parser will give you. So things like missing returns and functions and stuff like that. And it's also an extensible thing. So it can run at different times. There's some analyzers that can run as you're typing, but they got to be very fast or else the typing will slow down. But we also have different things that will run at builds and saves and stuff like that. So that's, again, an opportunity to alert users when they're violating rules. They can even do code formatting rules, API kind of constraints and stuff like that. So it's pretty exciting. And there's other features. Again, CDT is a very full-fledged environment. So we have code formatter. We have different views for showing different structures of your program. So call hierarchy showing functions calling other functions. And you can map that in a tree. So, oftentimes you basically would stick a breakpoint and look at the call stack to see where things came from. So, but you can do that statically before running it. We have a type hierarchy for include hierarchies, which of course in C++ is more complicated than Java since you have multiple inheritance and having to deal with that. We even have some interesting features like organize includes. that will basically analyze your code and figure out what includes you have to have. But our biggest challenge is that the standards are changing very often. It's really hard to keep up, and we don't have enough contributors to keep up. So we're actually falling behind as far as standard support goes. So that's why we started looking at language servers. Can we find a bigger community to provide us the same capabilities that we have with CDT, but with a group that can keep up with the standards? So that's where we got us into language server protocol. I think by now a lot of people know what that is. It's basically a way to create a language server and be able to extract these server features, all the things I talked about. And it's, it's not complete. There's stuff missing from there that we need to look at. So clangd is the main one that we've been looking at, or at least I've been looking at. It's part of the LLVM Clang project. It's great in that it's in trees, so that you have full access to all the utilities that LLVM provide for, because you have access to the compiler itself. So including the compiler drivers that set up things like the built-in includes and include paths, because Clang can plug into many different environments. So it's fairly fast too, and it's also, you get to great diagnostics from Clang. I don't know if you've used Clang and GCC, go back and forth. Clang's error messages are way better, and it actually gives you suggestions on how to fix things, and the clangd environment has support for that. But clangd doesn't have an index, which is very bizarre. It's the thing that in CDT we started with an index because we figured we'd need that. But it's coming. There's one coming. There's a group from Google that are working on it, and they're working on adding one. But at least it remembers when you look at different files, it does keep track. So there's the beginnings of it. It's also very hard to extend. So if you have an environment that Clang doesn't have support for, so our QNX environment was an example. There are strategic places in the Clang code where you have to add support for that. But it kind of means you need to fork Clang or push those changes upstream, even though they're kind of half-baked. So it's a tough challenge. There are a couple other language servers that are also built based on Clang, but not in tree. They use the Clang library and a bunch of hacks at how to get at other code that's in there. CDT, basically this summer we produced the language server protocol. Kind of taking advantage of that and hooked Clang and cquery, the other one, up to it. I can show a quick demo of that. So this is the LSP4E version of it. You do things like, it has the diagnostics. So those are messages coming from Clang, the compiler itself. It actually has the ability to do quick fixes, which is cool. Control click, so you can see the header files and stuff like that. And the cool thing is, again, it's a language server protocol. So if you want to do this in other environments, other IDEs, so this is Visual Studio Code, the same code, and again, you can get the same features. And interesting enough, I've been playing with this lately, that you can also get it in Thea. So this is Thea, and it's got the same, since it's using the same editor as Visual Studio Code, again, it's got the same kind of features to it. So that's the benefits of language server protocols, being able to do that. So kind of to wrap up, where do we go from here? So we're definitely going to invest more of our time in these language servers. Invest time in LSP4E to make sure that it gives what we need. And really adopt the new IDE architecture. So CDT is going to have some dramatic changes over the next few years. As we move to these architectures where we're sharing components. So in language server kind of starts us down this path. There's the debug adapter also is very interesting to us because we have a really complicated debug system and then we'd like to have something simpler. So we're actually going to build a debug adapter for GDB that can plug into Eclipse as well as other IDEs. And again, make sure, and we need to reach feature parity with CDT at some point. So if there's stuff missing from the debug adapter protocol or the language server protocol, we need to figure ways to catch up. And builds, again, we're going to take a look at, basically try to externalize all our build systems. So again, they can be shared with our other IDEs. And that's really the point, is provide our users choice. And, make sure Eclipse in the new architectures, we get there and really take the expertise that we have in C++ and actually work with these other IDs. We're actually talking about doing a Visual Studio Code extension for our debug adapter that we build. And looking at Thea to see how we can, and Schaefer people have been on us to, come try and help. So that's kind of things that we want to do. And really to give our users choice and make sure that, they need the features of a C++ development environment, but the front ends don't always match. So Eclipse, there are a lot of haters of Eclipse in the C++ world. A lot of people that love it, but make sure that we can give them those features, but let them choose what kind of front end they want to use. And that's it. 2 minutes over. It's a lot of slides to get in, so I'm sorry. It was a rush. Any quick questions before? Yep.
You mentioned that there were features missing in your opinion in LSP. What kind of features would you see more?
In LSP? Well, there's things like, and actually cquery has implemented some of them. Things like call hierarchy. Like it's pretty basic. It's fairly young too. Like it has the great features like content assist and finding declarations and doing searches. But when we want to do some, more in-depth analysis, like building a call hierarchy, refactoring, it doesn't really have anything to do with refactoring. So as we figure out how you architect that, we may need to extend the protocol, and cquery has done that. But then working with Microsoft and see if they would want to adopt these things to the protocol.
The design stage, not at the proposal stage.
Yeah, we're still really just experimenting. We're almost at the prototyping stage. But as we get it going, it's becoming exciting. Like the clangd environment works really well for what it does. So content assist is fast. A lot faster than I thought it would be. So CDT does a lot of cheats to make us fast, but clangd's got, it's got the full C Clang compiler there, but they've managed to figure out how to make that fast too. Sure.
You mentioned the DAP, so
yep.
Are you planning to make a debug adapter that would be on par with what CDT already does?
So the objective is to make a debug adapter that's on par with CDT's existing debug integrations. Yeah. Yeah, it's basically, it's got to be as feature. If we're going to replace the features in CDT with these new things, we can't. We got to be there. We got to be at the same level. Okay, thank you.